this, right? Negative 2 comes out, so positive 4, x to the negative 3, y to the negative 3. Now look, we may need to drop those negative exponents down when we start evaluating, but at least for now, those are our raw derivatives there. Now we got to do critical points, right? Let's see where the partial of f with respect to x is equal to 0. 2x minus 2x to the negative 3, y to the negative 2 equals 0. And then the other one, partial with respect to y equals 0, is 2y minus 2x to the negative 2x to negative 3 equals 0. So setting both of those equal. Y to negative 3. What's going on, man? Maybe this monster is messing with me. Thank you. All right, those look pretty bad, don't they? But just remember, those negative exponents just mean we have fractions there. What do you think? You want to try and set them equal to each other? You want to? Maybe we should just write them out first. Let's write them out as fractions. So this is 2x minus 2 over x cubed y squared equals 0, right? That's really what that means. And then over here, it's similarly 2y minus 2 over x squared y cubed equals 0. I have an idea. Maybe I'll get common denominators, like on each side. Like, let me get a common denominator here, put them together. Huh? If I do that, I have to multiply the top and bottom of this by x cubed y squared and do it on the bottom, x cubed y squared. Well, that's a good marker. So this will become 2x to the 4th y squared, right, over the common denominator, minus, let's put them together now, 2 over all of that, right? Pardon me? I can do the same thing over here. Let's see, this will become 2x squared y to the 4th minus 2 over x squared y cubed equals 0. So I'm doing the exact same procedure, getting common denominators each side. Now the only reason I did that is because the only way that a fraction can equal 0 is if the numerator is 0. That's the only way a fraction can ever be equal to 0, is if you set the top to 0. So, pardon?
That's pretty smart.
Yeah, so let me do that. So I'm going to do this numerator, 2x to the 4th y squared minus 2 equals 0. And over here, similarly, this becomes 2x squared y to the 4th minus 2 equals 0. And I don't know, I'm a pretty big fan of setting these equal to each other now. I don't know why, I just really feel like that'll take us somewhere. Are you all okay with that? Are you all okay with me setting them equal?
Yep.
Or no? If I set them equal, won't the 2's go away? Yeah? Okay, so if I set that equal to that, then I'll get, you want to divide? Okay, let's divide by 2. X to the 4th y squared minus 1 equals 0. Or you could say x to the 4th y squared equals 1, right? And then here you could say x squared y to the 4th equals 1 this way. Same thing, divide by 2. And if they're both equal to 1, they're equal to each other, right? If they're both equal to 1, they're equal to each other. So set these equal, and you get x to the 4th y squared equals x squared y to the 4th. Do not divide both sides by x squared y squared. Do not. Move everything to one side and factor. So x to the 4th y squared minus x squared y to the 4th equals 0. Pull a GCF now. What's our GCF? X squared y squared. And that leaves you with x squared minus y squared equals 0. which is the same as x squared y squared times x plus y times x minus y, difference of squares equals 0. I think we have our different possible answers here. I have x is 0, right? So I can have x is 0. I can have x is, oh, y is 0, sorry. Y is 0. X is y, or x equals negative y. That's me just setting each of these equal to 0, right? Set that equal to 0. X squared equals 0 only when x is 0. Y squared equals 0 only when y is 0. X plus y equals 0 only when x equals negative y. And x minus y equals 0 only when x is y. Okay. I got to figure out, these are 4 different scenarios, okay? So let's go look at the first scenario. And I think what I want to do is I want to leave one of these up here. Let me leave this one up here. Can I leave that right there? I'm going to leave this one here. This one right here. Because I don't have a point, I don't have any points yet, do I? I just know that if x is 0, I've satisfied it. If y is 0, I've satisfied it. If x is y, I've satisfied it. If x is negative y, I've satisfied. So let's go with the first, yeah, I'm keeping that one there. Suppose that x is equal to 0. If x is equal to 0, take this equation. You can take any of your equations, but let's take that one. If x is equal to 0, right, then what? It's not possible. It's not a solution. Now, how do we know that? Well, look, 0 is not even the domain of the original function. Do y'all see that? We couldn't plug 0 in to begin with, right? Yeah. So if x equals 0, nope, okay? Not in the domain. So we're not even going to consider that, right? Yeah. Okay. What if y is 0? Same thing. Nope, not in domain. Nope, not in domain. Domain of f. Okay, so we can eliminate those. Now, what if x equals y? Now, if x equals y, then let's go into this. And let's replace y with x, right? Then you get x to the 4th, x squared equals 1, which means that x to the 6th equals 1, which means x equals 1 and negative 1. Right? Which means we have what points? X can be 1 and y is the same thing. Or we could have negative 1 and then y would be the same thing. So I have 2 critical points so far, right? So far. Questions there? So these 2 didn't work. When I let x be y, we have 2 critical points that come from it. I have one more thing to consider. So I've got that, check. Let's let x be negative y. If x is negative y, or y is negative x, however you want to say that, what does this equation become? X to the 4th. This is negative x squared equals 1, right? Because we're replacing y with negative x. Or, yeah, y with negative x. But that's the same thing, isn't it? That's still x to the 6th is 1, which means x is plus or minus 1 again. You have a question? Come on. Which one? This? Oh, shit, I erased where that came from.
So what we ended up doing was 2x to the 4th y squared minus 2 equals 0.
We got a common... we divided by 2. Yeah, I don't know where... It's been a while. But it was one of the equations. I think... Can you show?
Yeah. So we're at this point. We factored out a 2. Right.
Yeah, we factored out 2, and then we moved things over, yeah? Okay, we moved the 1 over. So remember how we got these 4 different conditions here for our critical points? What I'm doing is I'm going back to any equation we had earlier, and I tried to pick the cleanest one I could see. Like I could have picked any of them, but I picked the one that looked like the easiest to work with. All right, be careful here. because this gives us the same two x values, right? It says that x can be 1 and y can be, x can be 1 and x can be negative 1, right? But what's y? If x is 1, what's y here? Negative 1, because we're going under the assumption here that if x is this, y is the opposite. So this is 1, negative 1, and then negative 1, positive 1. See? They're opposites. Under this condition, the x and y values are opposites. So now we got that. So we have how many critical points? 4 critical points. We have to calculate D for all 4 critical points. Yeah. Okay, here we go. The good news is that they're all 1s, right? So when we plug them in, it should be pretty easy. We'll see. We'll see. So our critical points, just so I can have them listed over here, my critical points are 1, 1, negative 1, negative 1, 1, negative 1, negative 1, positive 1. Those are my critical points. I have to calculate D for all of these. D of 1, 1. Let's do that. Well, that one, here's my second partial, right, with respect to x. If I plug in 1, what's 1 to the negative 4? Still 1. 1 to the negative 2 is still 1, right? So we get 2 plus 6 is 8. 8. Okay. Plug in 1, 1 into FYY. 8 again, right? Minus, okay, partial with respect to x, then y. Plug in 1 here and 1 here. Just get 4. 4 squared. That's positive, isn't it? 64 minus 16? Positive. Okay, when it's positive, what do we need to look at? fxx. So since that's positive and this right here is positive, local min. Local min. At 1, 1. And if I plug 1, 1 into the original function, I think I get 3. Okay, there we go. We got 3 more to test, right? D of negative 1, negative 1. Okay, be careful here. Does it change anything? Do we get the same answer? Remember what it means, right? Negative 1 to the negative 4, right? Negative 1 to the negative 4 just means 1 over negative 1 to the positive 4, right? So that's still 1. So we get the same thing, 8, right? 8 for both. And then does it change this? This is, well, it is a little different because what's negative 1 to the negative 3? It's still negative 1, but then we have another negative 1. So it's still positive 4. But just, we should note that it's, I don't know why I put equals there. 4 to the second. So still, it's positive here. And hey, isn't this still going to be a local min? And it's the same thing, right? But negative 1, negative 1, 3. All right. 2 more. D of 1, negative 1. All right, I think we still get 8, right? Because it doesn't matter because these are both even powers. It doesn't matter if I plug in a positive or negative. So 8, 8. And does it change the other one?
Yes.
It does, but we're going to square it, right? So it doesn't matter. Negative 4 squared. So still greater than 0? And now we look back here. Local min again, right? Are we going to have any local maxes, you think? 1, negative 1. And is it still 3? Is it still 3? Yes, because everything in the function is squared. So, okay, last one. It's the same exact thing. Negative 1, positive 1. We still get 8. We still get 8. We still get minus. But this is negative 4 and squared greater than 0. And that's greater than 0. Local min again. At negative 1, positive 1, 3. That is a weird, this has got to be a pretty weird looking graph, huh? Well, maybe not, just like 4 points where you have low spots, right? Okay, can I erase this? Yeah. What are you all seeing as like potential issues here? Solving the equation, like finding the relationship, I guess, maybe? The concept's pretty straightforward though, right? Like what you have to do. Here's the picture. We have asymptotes, right? Anywhere x is 0, the thing was undefined. Anywhere y was 0. So along the axes, you can see we have this like asymptote, right? What we just found were these low points on the bottom. Right there, 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 there. See those 4 low points? The bottom of the graph, we found those 4 low points. Let me see. So this is the one that I offer for bonus. For those of you who may have done not as well as you thought or wanted to on a mini exam, you can try this one, okay? Turn it in. I don't know. What do you think? Give you a week? Give you a week, next Monday?
This is the one where d equals 0?
I think so. I'm pretty sure that, well, there's going to be a few different points, I believe, on this one. But there's one in particular where, yeah, and you know, if you don't get that, that's okay. I just want you to see like you're going to run into something weird there. See how it goes. All right. We're going to move on. We have about 15 minutes left. We can at least get the concept going now. So what we're going to do now is we're going to shift gears, right? That's how to find local max, local min. There were no domain restrictions on our functions, right? No domain restrictions. Now we are going to restrict the domain. And remember, these are surfaces, right? So the domain is on the ground, you know, in the xy plane. The z is up here. So before we can begin restricting domains, we need to define something. The difference between what's called a closed set and an open set, or sorry, closed and not closed, when you're talking about a set in two-dimensional space. So on the ground, think about a set of points. A closed set is going to look like this, right? All the points are here, and all the boundary points are included in that set. Just like on a closed set in two-dimensional space, on a number line, you needed the 2 endpoints, right? They had to be filled in. Same idea, all the points inside and the boundary. Here are some examples of sets that are not closed. Does not include the boundary. Includes almost the entire boundary, missing 1 point. Here, no boundary, but here, including boundary. These are not closed, those are closed. Now, we also need to understand what's called a bounded set. So, y'all understand the idea of kind of a closed set? A bounded set is any set that you can look at all the points and you could draw a circle around them and include everything. So if you took like half of a plane, that's not a bounded set because you couldn't draw a circle around it and contain the whole thing. So any set that you can draw a circle around and contain the set is called a bounded set. So closed is one thing, bounded is something else. All right? Like this right here. Let me draw this. Is that closed? Yes? It's everything in there and includes the boundary, right? Okay, it's a closed set. Is it bounded? Well, can you draw a circle around this and include everything? Yes. Okay, so that is a closed bounded set. Okay, is this closed? No, that's not closed. Is it bounded? Yes, because you can draw a circle and contain everything in it, right? Okay, is this, let me see, I'm trying to think how when it is. Well, like I was saying before, if this is the xy plane, if I just take everything in the first quadrant like this, is that closed? No, because it goes forever, right? It doesn't contain a boundary. All right, is it bounded? No, it's not bounded. You can't draw a circle and contain everything because we're assuming it goes forever, right? All right, they're just two different ideas. I want to make sure you understand they're two different ideas. Now, the theorem we're going to have is only applicable to closed bounded regions, or closed bounded sets. All right, closed bounded sets. And this is where I like to interject a little bit of history. But as I get older, people know less and less about this. Ted Kaczynski, right? Who's Ted Kaczynski? Y'all know who he is? The Unabomber. Do y'all know what he did? Anyone? Y'all know what? Y'all know? Who knows the Unabomber? No? So he's famous for being one of the first terrorists. What do they call homegrown terrorists? Domestic terrorists. So he was sending bombs in the mail to people. They would open them up and blow them up. He killed a few people. Or he'd just go put a box like in a parking lot. People, oh, what is it? Blew them up, right? So he was making these bombs. Ted Kaczynski, he was actually a mathematician, and he was studying what's called the boundary value problem, which is the value of functions along these boundaries where you don't have closed. So we're looking at closed bounded. He was looking at things that aren't closed bounded, and things behave differently there. And so you have to pay attention to a lot of different things. I'm just prefacing that because everything we're doing, our domain is very nice, right? Very nice. If we step away from that, it becomes more challenging. It turns some people crazy, apparently. I don't know. No, he quit doing math. I mean, he quit math. He dropped out of school. He was very bright, and then just went and lived in the woods and started sending bombs to people. Yeah, yeah. All right. So what is the theorem we have that allows us to find the absolute highest point and lowest point on a surface if we're restricting it to a closed bounded set? You have to imagine that if your domain is a closed bounded set, then won't your surface be finite? Like it'll be a finite surface up there. It doesn't extend in every direction anymore, does it? So we should have a highest and lowest point. So the theorem says, here it is, the extreme value theorem for functions of two variables. So if f, if your surface is a continuous surface, so it's nice, there's no like weird breaks in it, on a closed bounded set, then first of all, it must reach a highest and lowest point. It has to attain an absolute maximum, and it has to attain an absolute minimum, right? And we are going to try and figure out where those are, where they happen, and what that highest and lowest point is. Here's how to do it. To find the absolute maximum minimum values of a continuous function on that closed bounded set, what we do is first, step one, is we find the value of f, the original function, at the critical points in D. Okay, we were just doing this. We were just finding critical points, right? We are going to do the same thing we just did, but we are not going to calculate this anymore. Okay, what we're going to do is we're going to find the critical points, and we're just going to plug those into the original function and see what we get out. This is the analogy is when we were doing the closed interval method in Cal 1, we had to check the endpoints, right? And we had to check on what's going on the inside. This step one is us checking what's going on the inside. Then we have to check the endpoints, right? That's step two. So we have to find the extreme value of the function on the boundary. That's going to be the hard part. Because when you plug in two endpoints, it's just two endpoints, right? But how many endpoints do you have along a boundary? Infinitely many, right? So that's going to be a problem. Okay, let's do it. Find the absolute, we have time to at least set this up. Find the absolute, well maybe not, hold on. We can at least do the first part. Find the absolute maximum minimum values of this function on the closed triangle with these vertices. So I'm going to draw this triangle over here on the side because I don't want to have to erase it. We have a triangle with vertices 1, 0, and then 5, 0, and then 1, 4. we have this triangle. This is our domain D. Don't confuse this with capital D from the previous part of this section. This is not the capital D we were calculating a second ago. This is the domain of this function. So imagine on the ground. Do y'all see that triangle on the ground? Y'all see it? Imagine we have a surface, right? The surface is this function. But we are restricting that surface to just the points coming up from that triangle. So here's what this looks like. Here's the surface just in general, right? There it is. But what we're going to do is we are going to restrict it to that triangle. I need to make this a little smaller. We're going to restrict it. So there's a domain written in 2-dimensional. There's the domain in 3-dimensional space, right? Over there. Imagine just allowing yourself, there's the surface, okay? You're just plugging in the points from that triangle into the surface, and you would just get the green part of the surface. Does that make sense to y'all? We're only looking at that green part, and we're saying on that green part, what's the absolute highest and lowest points? So I'm just going to take the original surface completely out, and what we're looking at here, the green is our original surface restricted to that triangle domain. And we are trying to find, we are trying to find those points, and what we're going to do is we're going to figure out, which of those is the highest and which is the lowest, all right? So let's at least do the first step of this, all right? The first step of this is to just find the critical points, all right? So I'm going to put here step 1, find the critical points. How do we find the critical points? Figure out where the partial of f with respect to x is 0. Figure out where the partial of f with respect to y is 0, right? Wherever that happens. Okay, these should be pretty straightforward. What's partial with respect to x? What is it? Y minus 1? Set that equal to 0. Do you all agree with that? Derivative of this with respect to x? Y minus 1. Okay, over here, partial with respect to y. X minus 2 equals 0. Clean solutions, yeah? 1 and y is 1, x is 2. So this is the point 2, 1, right? What I need to do is I'm going to need to plug that into the original function and see what it spits out, and then compare that to what's happening at other places along the boundary. Now, we do have to check, is 2, 1 in here? 2, 1 must live in here, though. It does live in here, right? 2, 1 is somewhere in there? Okay, so that's a critical point. That's a critical point. And it's in D, right? It's in D. So that means I want to take that critical point and plug it into the function, the original function. And let's see what we get. 3 plus 2 times 1 minus 2 minus 2 times 1, I believe. What is that? Is it 1? We get 1. Okay. Again, I did not calculate capital D, right? This is a completely different method from local max, local mins, where we don't have domain restrictions. Here, we're trying to find the absolute max and min. The first step was to find the critical points, or point, make sure it's in the domain, and then just figure out the function's value there. I have no idea right now whether or not this is a highest point or lowest point or neither. All right, I have no idea. What I need to do now is work and figure out what the value of the function is along the boundary, and that's going to be the hard part, right? Like we said, there's an infinite number of points around the boundary, so how do we do that, right? Come to class next time, and I'll show you how we work our way around the boundary. All right. For now, though, this is a question mark. We know that this point 2, 1, 1, right, could possibly be an absolute max or min. All right, everyone. Have a good rest of your day. Yeah, it should be right there on my desk.